Good morning and welcome to this presentation. My name is David Noel. Today we'll be looking at facial detection and tracking in videos. The objective of this presentation is to compare some of the tracking algorithms for tracking faces in videos. The three most important algorithms today are the Canady-Lucas-Thomas, also known as KLT, the Kalman filter, and the CamShift algorithm. So what is facial tracking? Well, facial tracking, as we see, is the process of identifying a person's face and tracking that face over successive video streams. Some of the applications might be in traffic monitoring or targeted marketing, for example. Some of the difficulties with such a process is the face may be too occluded, there might be too many faces present, or the images of the faces may be too small. And another huge factor is reappearance. That is when the face comes in and out of view. The first algorithm, the Canady-Lucas-Thomas algorithm, or KLT, is used to identify and track features within images. It was developed fully by Tomasi and Canady, building on work that Canady and Lucas had done previously. It is computationally inexpensive, but one of the drawbacks is that it is poor at handling occlusions. The KLT algorithm can be accomplished in three sections. Number one, we can detect the face. We use the Viola-Jones algorithm, a very well-established face detection algorithm. Secondly, we locate the facial features to track. The first way we do that is by finding what is called the Harris corners. And when we find the Harris corners, we basically get back two eigenvalues. We find the minimum of the eigenvalue, check to see which of those minimum is greater than a threshold value that we set, and whichever minimum eigenvalue is greater, we set that as our feature point. The third step, now that we have our feature, is that we start tracking the face by using a displacement D. And the displacement is calculated by using the Newton-Raphson method in our case. This displacement basically tells us where on the next frame the feature in step 2 is going to be located, or most likely be located. So we look at the KLT in action. This was the GUI that I created for this project. And as you can see, the face was detected. Here we have a beautiful pattern of the features that was detected. We can see the success and the failure rate to the end. And this is a live video of myself testing the algorithm. It is a very robust algorithm for, most cases. However, one of the biggest drawbacks, as we probably saw there, is that whenever the face went out of view, the algorithm could not reacquire it. That's one of the biggest pitfalls of this algorithm. Then we move on to the Kalman tracking. Now this is another algorithm that is very popular and is very, very flexible. It was developed between 1960 and 1961. It models a linear system. The basic idea of the algorithm is that you input some noisy data and it tries to minimize that noisy data as much as possible. The penalty, however, for using this algorithm is that it poses significant delays. Let us take a look at the algorithm in more detail. In order to use the Kalman algorithm, the first thing we need to do is to create a model. The first line at the top gives us our position model, or our process model. The second line gives us our measurement model. So once we establish a model to be fed into the Kalman filter, we can continue on to step 2. Step 2 says we're going to start the filter process by setting initial values. So now we have our model from stage 1. We are now going to initialize that model with some initial data. Now, one of the most important steps here is to keep the noise and the noise related effects to a minimum. For example, in step 1, the process noise is given by WK and the measurement noise is given by VK. We need to keep those as minimal as possible. Those would make the greatest difference in use of the algorithm. So now that we initialize the model in stage 2, we start the iteration process. That is, we feed in an initial value that gets updated in the time of the section, and it gets corrected in the measurement of the section. This gives you a brief idea of the Kalman algorithm in action. So, as we'll see, it first of all identified my face, and based on the model I inputted, the model was based on constant acceleration. It started tracking my face, and it had a relatively good success rate at the beginning. It's about 90% starting up. And as I start moving my face, it starts tracking me as it should. However, you might notice that the video has a slight delay. Earlier we talked about the Kalman algorithm is computationally intensive. This is what we were talking about. It's a bit slow. However, one of the greatest use for the Kalman algorithm is the fact that when I move my face out of view, look at this, it retracts my face when my face comes back into view. There we go. Unlike the KLT algorithm we saw previously. So this is one of the biggest uses for the Kalman algorithm. After Kalman, we are going to move on to the Kamshift algorithm for tracking. Now the Kamshift algorithm is a modified version of the min-shift algorithm. It handles dynamic processes and changes, unlike the min-shift algorithm, which only handled static processes. It tracks the face's hue using a probability distribution of the face color in the HSV color space. It has very fast reaction time, and one of the drawbacks is that you can have reduced accuracy if there's a little distinction between, let's say, the background pixels and the skin pixels. It wouldn't be able to tell the difference. The algorithm. The first thing about the Kamshift algorithm is that we will choose a window size, let's say S. Then we would center that search window at a data point, let's say PK. Then at this point we have our window. We will compute the centroid of that window using this formula. This formula is known as the zeroth moment formula. From that calculation, we would get the basically exact location of the centroid of that window given by x sub c and y sub c. The fourth step, once we have the location of the centroid, we would center the window at the centroid, and we keep repeating steps 3 and 4 until there is a convergence process. That is when some function of pk is approximately equal to 0. So let's take a look at the Kamshift algorithm in action. There is a face detected, there's a silhouette on the right hand side, and if you notice, it started on my nose initially. That's part of the programming. I used the nose part to try to keep track of the face. However, as it goes along, you notice it started focusing more along my forehead. So at this point, it's basically having some difficulties distinguishing between maybe my skin tone and the background color. Now as I move out of focus, look at what happened. It cannot readjust itself to retract my face like the Kalman did. So in this respect, the Kamshift and the KLT algorithm acts very similar when faces move out of focus. So as they are, they cannot really handle occlusion properly. So at this point, we will come to the conclusion of this presentation. In conclusion, we can see that the KLT algorithm yields significant tracking accuracy which deteriorates, however, in the process of occlusions. As we see, when I move my head out of the focus and back in, it cannot retract me. The Kalman algorithm also yields substantial accuracy even in the presence of occlusions. However, its Achilles heel is it lacks speed. It's very computationally expensive. And the camshift algorithm is the fastest and the most reactive, but it is the least accurate. So some recommendations to improve the performance of the algorithms. The KLT can reduce occlusion effects if edge detection is performed on every frame instead of just the first. Now for the KLT algorithm, when it determines the features, it only determines the features on the first frame, but all successive frames, it does not recompute the features. That, if it does that, it can basically overcome most of the effects of occlusion. Kalman can increase its speed by using maybe functions to replace matrices and Jacobians to define affinity. If you had noticed prior, the Kalman algorithm uses basically hard-coded matrices to represent its states. Using functions can basically provide a more continuous flow and faster updates. And also Jacobians can be used to take affinities into consideration. And the camshift's accuracy can be improved by using maybe the YCBCR color space instead of the HSV color space. The reason is the YCBCR color space, it more accurately represents human skin and the color of your skin and the color of your flesh. So at this point, I'd like to thank you for your time. Any questions or thoughts or comments, please feel free to contact me at my address, my email address at the bottom, atlanticstar@ufl.edu. Again, I'd like to thank you very much for your time. I hope you enjoyed this presentation. Thank you.